Yeah.
Okay.
Okay. I just have some announcements at the start. First of all, welcome everybody. Glad to see you here today. Um, my name is Rosemary Walling, and today Alan's gonna give part 4 of his Planetarium's Educator Workshop. You can get the recording on YouTube or on the Pacific Planetarium Association website. I will put the links in the chat. Next month, August 28th, we'll have Julia Plummer talk about light pollution and using the planetarium to motivate audiences towards action. That will be August 28th at 11 a.m. Pacific, 2 p.m. Eastern, and 1800 UTC. So if you would put your name in the sign up, which is in the chat. We just like to know who you are and where you're from. Helps to build a community, and also if there's any follow-up that we might want to do. We don't have a set time for an end. We'll end when the discussion is pretty much over. If we're still going at the hour, we can stop and let people say goodbye if they want to. So Alan is a fellow of the International Planetarium Society. He received the IPS Service Award in 2024. He's also a member of the IPS Education Committee and active in PPA as a treasurer for many years, and he's director emeritus of the Lawrence Hall of Science Planetarium. I probably did not have to say any of that because I think everybody knows Alan Gould. So anyway, thank you, Alan, for doing this.
Okay. Thank you, Rosemary. Um, and good morning, afternoon, or evening to all of you. Uh, this is this workshop, module 4 of the series, is one that I don't believe has ever been done virtually. So bear with me if there's any. I guess I should put it this way. I need your help because it is a workshop. So I'm going to rely on some slides, though, that we will be focusing on. And let me put those up right now. Mm. So that's my now. That's my email address, and that's what Rosemary just told you. What we're doing now is based on the Planetarium Educators Workshop Guide, which is on the IPS website. It was originally, and these 3 websites are where you can find it. The one with the red "do not look at" that's an old URL that is no longer functional. So I will, and don't worry about writing these down because at the end I will copy that plus some other things and put them in the chat. And that will go posted along with the recording in on the website for the archive of this session. This is the cover of the Planetarium Educators Workshop Guide, which, well, as you can see at the very top, it was the International Planetarium Society Special Report number 10. That's the original thing that's available on the IPS website. Here's a table of contents. 7 modules. We've done module 1, communication, and module 2, a framework for examining planetariums. I will actually give a recap of the very brief recap of those, and module 3, organization patterns. What we're doing today is how the visitors see it, or as the title of this workshop, I change it to how the audience sees it. Then the other modules are questioning strategies, which, hey, you may or may not have seen it. The latest Planetarian has an article that I wrote for the education committee about questioning strategies, and it's based on that. But we will have a workshop of that later this fall, an actual live workshop. And then module 6 and 7 have never been done virtually at all. None of those have been done virtually. Just to do a quick recap, were any of you here for the first module communication? Is anybody right? Unmute, because I have a question. Do you what do you recall any takeaway from that?
Hmm.
Maybe that's a tough. Actually, that maybe that's an unfair question. That's a recall.
That
I'm,
was months ago. I can't remember anything.
Okay.
I
All right.
don't
Fair
remember
enough.
either, although I'm sure I absorbed some things, but
Okay.
I can't
Let me trigger your
reiterate
memory
it right
then.
now.
Let me just briefly say, we did a little game, right? And when this is done in person, it's as you see here. The presenter, who is me, will put a picture up on the wall, and then we divide up into little groups of three, or in this case three, and there are the people who are facing the picture, like these people here, are playing the part of an instructor or a planetarium presenter. And the people who are facing have their back to the picture and they're forbidden from looking at the picture. They are paying attention only to their instructor, and the goal is for the instructor to explain or to get their students to draw that picture. And we went through a couple of rounds with different rules, strict rules that you cannot look at each other's drawings, you cannot ask any questions, you cannot do this or that. And then we loosened a rule, like for instance, you can ask questions in the second round. And does that ring a bell? Okay. The takeaway it was supposed to be that having interactions with the presenter is much more effective than just being talked at as a lecture. Lectures can be really great. If there are some really good lecturers around. So, module two, we were looking at the three basic ways to look at planetarium shows through that they are composed of a topic, a student, and an instructor, or you can think of it as if it's a public show, it's a subject, audience, and presenter. Um, we thought of different aspects of that. In module three, we were looking at organizational patterns, and this is one of my favorite ones. Different ways to have your group structured. Okay, so the didactic being the basic lecture planetarium. Start. What do they call it? The sage on the stage. The lecturer in the center of the planetarium, or no, usually in the back of the planetarium. Can't even see them. Um, but we can break up into small groups, each group doing a task. We can have each audience member do a task, um, like find a constellation or something like that. There can be informal discussions, which is like a small group, but there's no particular task other than to discuss a subject. And then there's a group meeting where everybody is focused on the same problem. The instructor, though, is not at the center. They're just kind of guiding the thing. Um, Socratic is something that most of us don't do a whole lot, where the instructor asks questions and the students, there's a lot of back and forth with the presenter and responding. So those are different. These are some of the ways that you can look at getting audience participation in a program. Um, I would like to mention though that some of the things that we're doing in this workshop, which is how the students see it or how the audience sees it. Um, this applies particularly to live interactions and audience participation scenarios, but I believe many of the principles here will also apply to recorded programs. Okay, in other words, companies that create programs could pay attention to some of the ideas here. And there are 5 parts. This is like probably the longest module, and I think I'm a little ambitious trying to fit it all in. We'll see. We'll see how far we get. I won't try to cram it in, but we're going to first look at, do students have theories, frames of reference, scientific explanations, classification skills, and teaching approaches. So diving right in. Uh, well, our main goals here is to figure out how to know what students are coming into the planetarium with, assessing their knowledge and their reasoning abilities, okay, at the outset. And then getting concepts that are appropriate for the audience or the students if it's a school program. And then what techniques do you have? What things do you do? What activities or how do you talk about the subject that will actually be effective? Now I want to get started with just these three questions that were asked in a study that was done. This was a long time ago, but I would wager a fair amount of money that it applies today too. These questions that were asked of high school students in the Boston area. And to go through this, actually, can I ask for a volunteer to read the first question, then I'll read the what's the first I'll read the data that it's given about it. Do I
Okay,
have
I'll
a
go, Alan. How
okay?
long how long does it take the Earth to go around the sun?
Okay. Only 52% gave the correct answer of 1 year in this study. 30% of the students knew that it takes about a month for the moon to go around the Earth. And only 10% of the students were aware that the moon turns on its axis once a month. Okay, well, that's certainly true of the general public as well. Um, Ken, could you read the second one?
Sure. Why does the moon have phases?
Well, okay, this is probably one of the tougher ones. 62% of students believed it had something to do with shadows of the Earth or sun. And only 36% of students correctly understood that the phases were a result of that the moon moves around the Earth. Okay, so that's, and the third one, Ken?
Yeah, why do we experience summer and winter?
Okay, well, here only 43% of the students knew that the seasons had, well, 43% did have an understanding that it had something to do with tilt of the Earth, but then interviews showed that there were common misconceptions that mostly that the Earth is closer to the sun um, in the summer than it is in the winter.
Oh, I've got
And yeah,
I'm sorry to interrupt, but I've got a procedural question here. Was this done in the planetarium? Do you
no,
know?
this is classroom.
Okay.
This is
All right, never
classroom
mind.
study. Yeah, but these are classroom things, or these ideas are things we need to be aware of in the planetarium. Um, okay, let's see. Um, so people come into the planetarium with their own knowledge and things that they believe that they either know to be true or they believe to be true. And the meaning is constructed from what they already know and from new learning experiences, which is what we strive to provide. A good idea for people to in a program where you're actually doing, trying to do these things, is to have people share their ideas at the beginning about what they know or they think they know. And what that does is it helps people, it helps you as a presenter or facilitator to understand where your audience is at, where they're coming from. It also helps them to understand that there's not just one point of view. That it might help them start thinking about, oh, there might be other ways of thinking about this. And of course, this is a recurring theme that we'll probably have, is that asking a question is a great way to get people to involve them in a discussion. Now, in a big planetarium, that may be a little harder than in a small planetarium, but it's not unheard of. There's people who do that even in a big planetarium. And another thing that we will be exploring is that reasoning abilities of people develop at different rates. Not only dependent on age, actually, but mostly dependent on age. Um, okay, so students have theories. And we focus on this question: what is the shape of the Earth? Okay, and of course, most people say that yeah, it's round. That's anybody will say, oh yeah, the Earth is round. But what do they really? What are they thinking? Okay, what's really in their head when they say it's round? Well, they could be thinking, well, some kind of circular island that this is like the ancient idea that the world, their concept of the universe, philosophers, is that it's an island that people can sail around. Some people might think that you see pictures of the Earth, and so you think it might be a planet in the sky. It's where astronauts can go. That's something that children, and then some children will say that and I'm afraid that adults too, some of them would say that yes, the Earth is a ball. They will say that, but they'll wonder why don't people fall off the bottom? Um, or they might think that well, it's a ball, but we live in some kind of flat space in the middle. So those are common things. And there is this. This is studies by Stella Vosniad. I can't pronounce that name. Vosniadu, I'll say, and William Brewer. They've done studies about mental models of the Earth and the conceptual change that people go through. And one of their studies was that they did different grades of elementary school, and the first graders thought of the Earth as a flat disk, usually, or some kind of rectangle. Third graders were able to do something that they called a synthetic model. That means that they take what their original belief was and then try to synthesize it to what they're told by a teacher. But when you have a globe there and are trying to explain that the Earth is round, and so that's trying to synthesize those two ideas of where you're coming from and where the teacher wants you to go. That could result in the idea of two Earths, one that's flat that we live on, and another one that's ball shaped that's in the sky. Um, and then by fifth grade, they found that about half had more scientific mental models. Um, okay, so we created. Now this is a classroom. This was a classroom situation, which from what we call a GEMS guide. It was Great Explorations in Math and Science, which was a curriculum development project that created teacher guides. And there was one called Earth, Moon, and Stars, which became the basis of a couple of different planetarium shows that we created at the Lawrence Hall of Science. Oh, actually, no. The Earth, Moon, and Stars was derived from our planetarium shows. Um, but this one had five parts to it, this teacher guide. Um, One was imagining that you are, we challenged people, imagine that you were lived a long time ago when people believed the earth was flat. How would you have explained how the sun returns to the east every morning after setting in the west the previous night? Okay, now let's let's just take a moment and think about that uh, and focus on that. Um, Pretend now this is hard. Imagine that you are believe that the earth is basically flat and that how do you explain how the sun gets from the west where it's set to the east in the morning? Anybody want to venture an idea there?
Maybe it just turns off and sneaks back over to the east to get ready for the morning.
Aha. I like that. It turns off and somehow sneaks back over to the east. Okay. Any other ideas?
And maybe it like goes through a door and the door closes so you don't see it. and then it runs around the building and comes in the other door in the morning.
Aha. So similar, but a little bit more specific. Yeah.
I think sometimes it was a birth and death cycle that was represented by the sunset and the sunrise.
Oh, so the sun dies every day and is
Yeah.
reborn. Huh. Okay.
I mean, that's a long time ago, but yeah.
Yeah. Yeah. All these would have been a long time ago, I think. But that's what we imagine. We stimulate our imagination to think about, well, different cosmologies. Any other?
I think I'm trying to remember my oldest child when he was very young. I think that he thought somehow there was a give and take between the lights on Earth and the sun. So the sun would burn out at the end of the day, but then it would absorb the lights from Earth during the night when we turn on our lights, and that would recharge the sun. That doesn't explain how the sun ends up back in the east anymore. I
But
should have read.
that sounds like an important part of the story, though,
Yes,
actually,
doesn't it?
that it gets recharged by human activity.
Yes.
And that actually for a very young child, that is really common to put a human stamp on whatever they're trying to explain. Um, wow, this is great. Thank you. These are great ideas. And it's not just the ancients who are facing this, it's the young, young people with limited reasoning skills, but they do have theories. Question was, do people have theories? And they do. Um, the second thing, we were going to go in a little more detail on this one, a questionnaire about Earth's shape and gravity. The third part was observing moon phases for about 2 weeks. And this is something we can do really well in a planetarium. Way better than a classroom, because in a classroom you're you're dependent on assigning it as homework or watching it during the day at a specific time, and it might be raining. In the planetarium, we have our beautiful time machine and no clouds. But then the fourth part is to model the sun, earth, moon system with something that you're probably mostly familiar with, and I'll explain a little more later for those who have not seen it. Um, it's not a teacher demo, this model, but it's something that the students do uh, themselves to refine their mental models. And then the fifth one, we're not going to really go into much, but it's identifying constellations and seeing how they change their position and how things move. So let's look at this questionnaire. This is kind of an interesting thing. Get ready to put something in the chat here. Uh, which of these explanations explains why the Earth is flat in picture A and round in picture B? And, well, just put in the chat what you think. Um, okay, when we do after I should have put in that question before you started giving your answers so that we have a good record in the chat. But I see that most of you are giving the correct answer. Um, it's round like, or no, it's not round like a ball. It has flat spots. It looks flat because we only see a small part of it. Um, and this is, people who have, a certain level of reasoning will not realize, it takes a certain level of reasoning to realize that it's actually a huge ball. And so that's why it looks like it's flat where we're standing on it. Um, Okay, let's go to the next one. Pretend that the Earth is glass and you can look through it. Which way would you look in a straight line to see people in far off places like China or India? Um, let me write. Let me wait before you put your answer. Which way would you look? Um, A, B, C, or D? Thank you for people for responding here. And the what's common, when people think about which way to go to a particular distance place, you think of that you're going to get on an airplane or get in a car and go, so you'd be pointing sideways, east, west. Um, I suppose if you're thinking of getting an airplane, you'd go up. But we're asking here, where would you look? Um, so thank you for those correct answers. This one doesn't require an A, B, C, or D. So here we're gonna we have these not to scale people standing on the earth, and in this, when we have students do it, they will draw what will happen to a rock. They're each holding a rock. What happens with each of them when they let go of their rock? So here I could ask you to draw it, but we couldn't have a record of that. So I'll ask you to explain it maybe. What would happen to the rocks? You can unmute and if you want to take a stab at answering that. Nobody. What would happen to the rock when you let go?
From each person's hand, it would drop towards down to the earth, but towards the center of the earth. So all of the lines should be pointing in towards the center.
Okay, thank you, Amy. And all of us here are giving the scientific explanation that is scientifically accepted. But let me show you what examples of some of the kinds of drawings that you see from what the audience or children or some adults perhaps are thinking when you talk about round Earth and the nature of gravity. Okay, so some drew with the rock going all the way to the center of the Earth for some reason. That just goes all the way. And that actually corresponds to Aristotle's notion that the center of the earth is the center of the universe, and everything comes to rest at the center. Um, but Aristotle probably didn't have this in mind. But what another common thing that I alluded to earlier is that why don't people fall off the bottom of the earth? Well, if you let your rock go and you're on the other side of the earth, it would go down. And this is actually a frame of reference thing that we're going to get into a little bit more. That how do you, but it's not just frame of reference, it's what is gravity? What's the nature of gravity? Okay, and here's the last question in the questionnaire. This is probably my favorite one. Pretend that you're Superman dug a tunnel all the way through the earth, and you drop a rock from the North Pole. Draw a line from the person's hand showing the entire path of the rock. This is a little harder. Can anybody care to describe what you would draw for that?
Yeah, I would draw a line going straight down all the way to the other side and then coming back towards the person dropping it and not quite making it back up to their hand, would it eventually come into rest at the center of the earth?
Okay, why would it not make it back up to their hand?
Because of gravity, because the force of gravity has taken some of that away. So or friction. Sorry, friction would be I think the thing accounting for that. And
Yeah.
Amy's smiling, so I must have said something wrong.
Amy, you see something wrong? Yeah. No. Um, yeah, no, that sounds like a pretty good scientific explanation of it. Um, that most of us would agree with. And air, I didn't specify whether there was air in that. So that's a subtle, you know, you couldn't dig a hole without air going in there. So I think that's a reasonable assumption, Ken. But let me show you what some of the drawings are that students actually came up with. Okay, John actually has something that's kind of like what you said, Ken, but Sally had something more like what Aristotle would have drawn, where things come to rest at the center. Things tend to have a tendency to come to the center of the universe. That was his description of gravity, basically. So it would just go to the center and stay there. But there are some others that have Mark and Sam. I like Sam's because it just goes splat on the other side. Um, and then B, I don't know that's a very interesting thing that it just kind of slingshots around. These are all, people's theories. And the scientific explanation is this one that's on the right, which Ken just told us, and which is very similar to what John drew here. So that's um, in the Planetarium Educators Workshop Guide, which I'll give you the link to. There's a rubric that shows levels of understanding about Earth's shape and gravity that were used as part of this. Um, Now we're done with part A, and let me do a time check here. How are we doing? Not too bad. Um, the frames of reference is what we're going to do now. How do people look at frames of reference and how do they understand it? And we're going to look at, well, we we already looked at the Earth, why the Earth looks flat, and uh, and that is a frame of reference issue. That you have a very large sphere that looks flat when you're standing on it because it's so big, and that requires a level of reasoning that that is tough for early elementary. And we're going to look at three different situations: the Martian moon problem, uh, two views of spiral galaxies, and then a moon phase diagram. Um, Here's the Martian moon problem: Phobos and Deimos. They have they're two moons of Mars, and they have phases. If you're on Mars, those moons would have phases. So this is sort of an outsider's view of a scene or a model that's set up. In this model, what phase is each moon as viewed by that person that's on Mars? Um, and let me ask that question of you. Okay, I'm keeping that diagram here, but I want you to answer. Well, first of all, let me put in the chat Demos, phase of Demos. What phase is that in the diagram? If you were standing on Mars, which letter would it be? Okay, this is a pretty easy one. Um, okay, now let's go to Phobos then. Let me hold on. Don't do it yet. Let me put it in. Phobos. What phase would Phobos be in this diagram?
Yeah, third quarter.
Okay, well, I think everybody thinks it's a quarter. Is it B or D? Yeah, that would be the big question. And that's a, frame of reference issue. Uh, in fact, let's,
B,
yep, John.
B.
It'd be B.
Yeah.
Okay. Okay. Now you all are pretty good scientists here and give a pretty good scientific thing. Okay. So let me show you what some of the results are from a study that is done. Okay. With college students. Um,
Hmm.
the first three answered B. And the one said, I imagine myself on the surface. Two said, in my point of view, I just reversed what I saw. They were asked to explain why. Okay. And I should have asked you that too, to explain why, not just give it. Did I? Okay. Save some time here. I didn't ask you to explain yourself. Um, but the last four, well, at three, the college student three said, I put myself on Mars in my imagination.
Ooh.
And the last four answered D. Four said observing shadows on models. Five said the moon is moving towards the sun. And six, Phobos is in the direct sunlight, not in front of Mars. So what is the difference between the first three and the last three students? What would you say? Other than the first three are
Hmm.
right and the last three are wrong.
So the first three put themselves in a certain orientation and then reasoned from that orientation. Like the middle one was a different frame of reference from the first and the last, one and three, but knew that they had to reverse it.
Mm-hmm. They figured they reasoned it out. Okay. Any other comments on that? Why they're
Yeah, Alan, I mean, I get it, but the problem is you've got the light bulb. You can't make the light bulb further away like the sun is, but it looks like both of the moons are in gibbous phase, so it's a little bit misleading there. If you got it farther away, you'd be able to see where the terminator would be in that case. So I don't know how to fix that exactly. A bigger room,
Yeah.
I guess.
Well, John, you raise an interesting point there because what you're commenting on is the picture that I'm showing,
Right.
which shows them as gibbous. And our point of view, your point of view, is looking at this diagram. But the
Mhm.
question is, what is the person on Mars's point of view? So
Right.
that's the crux of the matter, actually. The people who are answering D are having trouble uh, projecting themselves into the picture and seeing it from that frame of. This is under frame of reference. They can't project themselves into that frame of reference.
It
And
sounds like
so,
you're suggesting that these people are not capable of formal operations. Like Piaget would say, well, formal operations, you have to step off the planet and look at it from another perspective. So that's a hard mental skill to develop. I guess we can do it through this exercise. So
Well,
I like the
and
idea.
thank you, John, because Piaget was a Swiss psychologist, studied differences in people's abilities to perceive situation from a different point of view. Okay, and some people could imagine themselves in a different frame, and others could only see directly from their own frame of reference, that is, looking at the diagram. So, what Piaget found is that for some people, concrete experiments can help them see, can help lead them
Yeah.
to a better line of reasoning. And this diagram here, again, it's you have to kind of imagine what's going on. Let me explain what's going on here. In this activity, you have pairs of students look at the moon, with the sun being in the background, and they're imagining themselves to be Mars and looking at the moon from different places. And they draw it, and then they swap places and draw it. So they can see that, oh, it, depending on where I'm sitting, it looks different. And turn that could be of help in helping the students see. So that's called like a concrete experiment to help people look at things and see different frames of reference. Um, and the level of reasonings, John, thank you for bringing up Piaget, because this is a summary of well, a kind of basic understanding of different levels of intellectual development. So for we call it egocentric when somebody can only imagine one's own point of view. Okay, and they can only, they're operating at an intuitive level, and but when we say egocentric, we don't mean that they're selfish or anything. It's just it's just that they're operating at that level where they can only see from their own point of view, which can be selfish in some which in some cases, but
Yeah.
that's not what we're talking about here. Um, so I mentioned concrete experiments, but there's a concrete level of reasoning that Piaget refers to, using the terminology concrete as a imagining another viewpoint, but only after having some kind of concrete experience. Okay. And then the level that we are all operating at as scientists or as advanced as planetarium presenters, at least I hope we're all operating at, is the formal level where we have no trouble imagining different points of view. Um, um,
Sorry, Alan, but I'm stuck. I still don't understand why D is wrong. But
why D is wrong?
yeah,
Let me back up. Um, how do I back up? Sorry.
I'm sorry. I'm stuck there.
Okay, I'm backing up. Okay, so okay, you're operating at egocentric level, Ken.
Oh
Uh,
no, oh no. Please don't report that.
okay, so just imagine yourself on Mars and you're looking at Phobos, and then think of which side the sunlight's shining on. That person right there is where you are. Is it your left hand or your right hand that's lit? Not your left hand or right hand, but on Phobos. Does that help?
Yes, thank you. That was it.
Okay, okay.
I just
So
couldn't.
it's a left hand, right hand problem.
Gotcha.
Okay, good. I'm glad that I could bring everybody on board here. I hope. Um, okay, so we have these egocentric, concrete level, and formal level of reasoning for the frames of reference. Now, here's a little cartoon. Some of you may remember the Wizard of Id cartoons. Uh, I'll let you read the cartoon for a few seconds. And at what level is the wizard reasoning in the second frame?
Formal.
Is that the formal level or?
Yeah, he's put himself in the place of being there instead of being where the observer is.
Yeah.
Does that make sense? I guess
Well,
it does.
when we go to the end and and the person dies, we realize that maybe the wizard was not being, maybe the wizard was acting as an egocentric.
You've forgotten an obvious inference, which is that maybe he's just trying to get rid of the assistant.
Yeah, right, right. Yeah, I think we've all done this, the left-right duality, um, where, oh yeah, that would be in fact, I've used this line from the cartoon a lot of times. That would be your left, wouldn't it? Yeah, or that would be my left. Your right, is that your right or my left? So anyway, if you get it mixed up, you're probably operating on the egocentric level. And if you get it properly, then you're operating at the formal level of reasoning. Now, here's another interesting question for a formal reasoning. Think of as a concrete reasoner, actually. Look at these pictures of two galaxies, and the concept we're trying to get across here is that these galaxies actually have the same spiral shape, but one is viewed from above and one is viewed from the side. The question is, what might be a good strategy to communicate this concept to a concrete learner or a concrete reasoner? Any suggestions?
Well, you could get a 3D model of the galaxy and then just turn it on its edge. So, you can show them how you get that edge on view.
Hmm. Okay, yeah.
Yeah, that's good.
Anybody else?
If you had one of those uh, AI, not AI, I don't want to say AI, but one of those digital graphic things which allows you to rotate around, you could show it that way too, from perspective, change the perspective for them.
Yeah. John, you're moving around a lot. It's
I'm sorry.
little bit
Let,
disconcerting, but
let me stop doing this.
Oh, it's cool.
If I can just share with you, and I'll stop moving. But can you see what I'm looking at here?
oh,
I
yeah.
had to get all these telescopes back to the planetarium in a week and a half, so I'm just organizing things. I'm going to sit down and enjoy the time.
Yeah.
I'm
Well,
trying to multitask, and I'm just kind of
it's
driving
okay.
everybody nuts.
That's okay, John. You can switch off your video and switch it on whenever you want. Okay.
Oh, let me try to do that.
Um,
I need to take a break. Okay, sorry about that. My bad.
I was
okay.
Could flip a coin.
Flip a coin.
Yeah.
Oh,
Yeah.
To
the
show.
model.
Yeah,
Yeah.
that's cool. They'll use the coin as a model. Yeah.
Correct.
I like that.
Okay.
That's
Any other ideas?
I was going to say in a modern planetarium, you could just fly around, look down at them, you could actually move. That's the beauty of being able to have a video system in your planetarium. You can just change your point of view, and the audience can see how it's being changed as you move.
Yeah. Now that's a high tech, very high tech model that a lot of planetariums have now. It's great.
I think I'd probably use a frisbee. It's big enough that people could see it.
Frisbee. Yeah.
Yeah.
or a pizza. A pizza would be great.
A lot of
Put it on
times,
there.
it's yeah. All these are great ideas. I it's like get a model. Sometimes it's good to have a person use their something that they have readily available, like their hand, and you could actually have people ask people to move their hand like this and like that, uh, and that would be another kind of model. Um, I'm a big fan of having people use parts of their body as models for illustrating things. Okay, here's a moon phase diagram. Some of you may have seen something like this before. And what is the level of reasoning required to understand this moon phase model?
I can remember as a kid being totally confused by this model, you know, until I realized, oh, this is supposed to be the point of view. You have to really understand what that outer um, circle of images represent.
Right.
It's complicated.
So
I
what
think,
level? Yeah.
well, I think it's college level. And even there they have problems, but it's the idea of left, right, plus also knowing which direction the person's facing, like facing down in this image.
So yeah. And in the Piaget terminology, it would be formal level reasoning that would be required. College,
Right.
high school. Yeah.
This is exactly why students in their introductory course to astronomy don't like astronomy. They don't get it. The diagrams like this in textbooks just are beyond their comprehension if they're not brought along correctly and to understand.
Yeah.
But yeah, very formal.
So yeah, and even somebody who is adept at formal reasoning would probably find a concrete example or experiment helpful in understanding this diagram, even if they're well within the formal reasoning realm. Uh, of course, the essential thing here is that in the inner part of the diagram, you're looking at it from an external view, sort of like above, and each of those individual things are an egocentric view of the moon at those different positions. So yeah, it's kind of confusing. But once you latch onto that, the diagram makes perfect sense. But it is a high level formal reasoning.
Well, it's really two diagrams being overlaid over each other and with no connection between them.
Yeah. How many of you have seen a diagram like this in your experience? Show of
Oh,
hands. Everybody's seen that. Okay. So it's good to ask a question if you have any doubt about whether, the reasoning level that your audience is at, it's helpful to ask a question, to get a sense of that, whether they're understanding it or not. And then you adjust your strategy so that you go to their level of reasoning as a starting point.
The other thing that's problematic about that diagram is that the sunlight looks like it's coming from everywhere on that one side of the diagram instead of, basically a point, you know.
Right.
Um,
Yeah.
so that could be
Sunlight is
very,
very
very
far away.
off-putting as well.
Yeah. The
Yeah,
sunlight is there, but the sun is very far away. Yeah.
right.
Yeah.
I think that's a hard concept for students, but that the idea of if something is far enough away, the rays come in parallel. And so when you have to put it on a compact diagram like this, it looks artificial.
Mm.
And that human being on there is just terribly confusing.
Not to scale, yes. Well, the human being represents that's kind of like our Martian moon picture that we were asking people to project themselves into. Yes, it's difficult.
and there's another level of complication there where you see the person standing. You can see where that person is standing in relation to the Earth's terminator. So the person standing at the 12 p.m. thing, which would be 12 noon, that would be, you can see that's the middle of the day for that person. And then 3 p.m., the crescent moon, he's along there. And then he gets to the terminator at 6 p.m. So that means that the sun is setting at sunset, and that first quarter moon is at the culminated in the south. And that's all like, yeah, it's like, it's just a lot of information that you have to kind of break down into different components.
Yeah, and this is a problem, especially for people. Oh, how that we run across this all the time, where people think that this moon is only visible at night and the sun visible during. There's songs. Songs where we got the sun in the morning and the moon at night. That
Yeah.
that song. In fact, I was walking along one day. This number of years ago. My sister-in-law was saying. I pointed out the moon. This was in the afternoon. There was a moon, and she said, "No, that can't be the moon.
That can't be right.
That's not possible." And she would not believe it. And so
Get the telescope.
it's kind of funny.
Run to your
Yeah.
lives, the moon is out of orbit.
Yeah. Yeah. Okay, so using these levels of reasoning for scientific explanations is also at the uh, egocentric level. A child will attribute motives and purposes to inanimate objects and make assumptions that human actions are responsible for things. We encountered this earlier in the workshop, actually, when we were talking about how the sun gets moved from the west to the east, or how that changes. At the concrete level, they can use more complex relationships to explain phenomena, and use some observations to revise their explanation. For example, the sun doesn't always rise in the east and set in the west because I have a compass and I saw that it doesn't do that. And then at the formal level, there can be more extends explanations to predict new observations, or compare explanations like, the seasons question. If the Earth really is closer to the sun in the winter, the difference must not be very great, or it would be hotter in the winter than in the summer. That kind of reasoning for an explanation. Now, this little drawing here, these are three drawings that are sample drawings that when a teacher asks her students to draw what the moon looks like. And after the students compared their drawings, she asked, if they're all pictures of the moon, can you explain why the moon has different shapes, different times? Okay, so here's here's some interviews that were done. And maybe we can do a quick table read here. Um, Dario, can I ask you to be Joe, who is an 8-year-old? And and let's see. And I need somebody to be an interviewer. Um, volunteer to be. Amy, could you be an interviewer? Are you up for that? Okay, you need to unmute.
Which Amy?
Oh,
I can
Amy,
do
Amy,
it.
you're a good Amy. Uh, Amy
Amy
Eric
spoke up. She
Prupsa.
gets the job.
Amy T.
I
How
was
about
going to
that?
ask the same question. So I'll
Yeah.
be Tina, if that helps.
Okay. Okay, hold that thought. Uh, Dario, could you start? And we're going to do a table read here.
It divides itself in different shapes.
Does it ever put itself back together again?
In the daytime. In the nighttime, it divides itself again.
Why
Crazy
is it
talk.
that you can only see this part pointing to the crescent or that part at a time?
Because it's been divided up.
Okay, what's our level of reasoning here for Joe or for Dario?
Pre-operational ego. Yeah.
Yeah, egocentric. Okay, I think it's pretty clear. Okay, Amy, you're Tina. Who wants to be the interviewer?
I can do that.
All right,
This is
Ken.
Ken.
All right, let's do our table read here. Amy.
Something like this, something like it's our planet or another planet covering half of it, or the sun or something covering parts of it. Yeah, our planet.
So how does our planet get up there in the sky?
Well, like I'm looking at it because the shadow of the Earth is on that part of it.
In this picture, where do you think the shadow of the Earth is?
There's no moon like that.
You've never seen a moon like this?
There's no such thing as that kind. It can only be curved because the planet's round and the moon's
Huh.
round. So the planet can't be straight on one side to do that.
Huh.
Okay,
Well, that's brilliant.
yeah, what level of reasoning do we have here for Tina?
She's got the ego at the beginning, and then she says something really cool at the end where she's recognizing that the Earth's shadow is going to be round when it hits the moon. But of course, she's talking about eclipses, but she's not making a distinction.
Yeah, well, that's really
It's like on the watershed there, you know?
that is pretty cool actually when you think about it. And it's a good illustration of how people are coming in with their ideas and their theories and they're applying them, you know, as wrong, sometimes wrongly and sometimes they're on the right track. Um, okay, I got a couple more. Who wants to be Derek, who's 9 years old?
I'll be Derek.
Derek, and who wants to be the interviewer? Todd, are you able to? Can you unmute and be the interviewer? No. Okay. Let's see.
I will interview again.
Okay, Amy T. All right. So let's do our table read then. Derek.
Because every month, the clouds come over half of it. And then when the moon is full, there's no clouds around it. In a year, then it goes back to normal.
Do the clouds stay that way all night, or do they move around so you see it all different ways in 1 month?
Oh, no, it stays that way for a month.
Okay, what is our level of reasoning here?
That's pre-operational. It's ego again.
Yeah,
This is
I
like,
think
but like from the interview from that movie, A Private Universe. That's what the kid had his idea that clouds caused phases, and
yeah,
it did not get shot down when he proposed it, and he kept that that personal view and put it into his theory.
Yeah, except that in a private universe, they were interviewing college students. Uh, or
No,
what?
actually, I think that was ninth grade. Yeah,
Oh, that was
that
ninth
was
grade.
ninth
Okay.
grade. It was some
Okay. All right.
it was some high school in the Boston area.
Yeah, I was thinking about,
Although the
yeah.
college students were just as bad. You're right. The college graduates were terrible at Harvard. It's like, oh no,
Yeah,
Yeah,
that was Harvard. Yeah.
that was
yeah,
for the
break my
seasons.
heart.
Yeah. Okay, let's do the last. Let's see what Herbert has to say here. Um, who hasn't? Who would like to do a run through? Mm. Hey, John Elford, are you there?
Sure.
You want to do Herbert? And
Yeah.
then as a Rosemary, could you do the interview?
Sure.
Okay. All right, John, go for it.
Because at different days, like a quarter moon, full moon, half moon, just changes its position.
How does changing its position change its shape?
Well, because, all right, if it spins around, a kind of fog or mist can get on this part, and it will sort of look like a quarter moon.
How does one side get light and the other side get dark?
Maybe because reflections can't see the dark side, the sun, but reflections can see the light side.
On here, pointing to the full moon, where is the dark side?
Ah, it's in back.
In this picture, pointing to the crescent, where do you think the sun is?
Over in this direction, like the sun is right here, and it's showing that part.
And he is pointing to the correct position for the sun. So what level of reasoning is that? Thank you.
Kind of all over the map.
Kind of a mixed bag because yeah, there's definitely formal reasoning going on here, but there's also like with the mist thing,
Yeah,
he's trying to incorporate an old model in his head into this new paradigm of how phases actually happen.
yeah,
So he's got retaining bits of the old misconception as and wiring it into the story of the new conception of how it actually works.
exactly. Yeah. But we can see that he's kind of on the right track going towards formal reasoning, maybe maybe in a concrete, like this student would benefit from a concrete experiment or model.
Yeah.
Um, okay. Um,
Let
more
me
Wizard
just
of Oz. Yeah.
pause for a second because it's 5 minutes after the hour. If you do need to leave now, it's fine. Say goodbye if you want to. We're knee deep into this workshop, I think, so it's
I
likely to continue.
I think we'll have maybe 15 more minutes if you are able to stay, and if you're not able to stay, there is a recording that you can see later.
Thank you.
So the Wizard of Id. Here we are again with the cartoon. But
Oh, the first one is BC. BC.
what uh what level is the explainer for the upper cartoon? The explainer.
Sassy.
Yeah, yeah, right. I think we have a different category here altogether, huh?
Fanciful.
Yeah,
He's formally reasoning, but he just has the idea wrong.
yeah. Formally wrong. Yeah.
I mean,
Okay.
yeah, because he points out no responsibilities, at the end there, like, hey,
Yeah.
yeah, who are
Well,
you to judge? Who are you to judge the whole?
that's
You
right.
know,
Okay. And the bottom one, let's read that one. We don't have to read it out loud. Just take a minute to read it.
Mm.
So is that what level of reasoning are we at here? It's pretty.
Well, yeah, this stuff with the fifth power, that's all. It's like Star Trek when they make up terms like tachyon emissions. It's like somebody's trying to make it sound sciencey, and it's not.
Yeah,
That's
yeah,
not it.
yeah.
Are they
Okay.
are they on the moon? It's lunar eclipse.
Yeah, there we go. Okay, so we have another case of we don't know. We have to make up a new level of reasoning here for the Wizard of Id. Um, okay, now going into the next section, we're going to talk about classifying things, and we do this all the time, like stars, planets, nebulae, objects in space. How do people perceive our descriptions of how the objects are classified? How does the audience perceive it when we try to classify things? So here's an example, uh, classifying galaxies. And just to get us started here at the egocentric level, uh, in classification, well, the young children can notice similarities and differences, but they can only classify. They can't really classify in any complex way. There's similarities and differences. At the concrete level, they can begin classification by a single trait and can sometimes arrange objects sort of along a continuum, see how it progresses on a continuum. And at the formal level, they can actually put together hierarchies of things and rearrange them fluently. So here's an assignment was to classify galaxies from pictures of galaxies. And student one says basically there are two kinds of galaxies, spirals and non-spirals. Spirals might be seen face on or sideways, and the non-spirals either elliptical or regular in shape. What level of reasoning is that? And this is a diagram.
Uh,
Okay, well, sort of sort of made a hierarchy here.
yeah, it's concrete in that respect. I mean, they're
Yeah,
just basically cataloging things. Do they make the connection that you're seeing it from different angles? I mean, a
right.
face down spiral and an edge on spiral are the same thing, but just seen from a different angle. I mean, so
Mhm.
there's a beginning of that.
Okay, so maybe at the concrete level,
Concrete moving into formal, but
moving
whether they
in.
make that step, I don't know. It's up
Yeah,
to them.
yeah. So actually, that's an interesting point. These are not strict, hard-edged categories. People progress from one to the next. Here's a couple more. The student two with the upper one says pictures in the bottom row are all spirals, and the pictures in the top row are not spirals.
Yeah.
Uh, the ones here in the middle are skinny, and the ones on the right are egg-shaped, and the ones on the left are rounded. That's kind of
Yeah,
that's sort of the more basic level of reasoning. And then student three, in order from nicely shaped galaxies towards more squiggly galaxies.
uh,
That could be sort of concrete level because they are arranging it in a kind of continuum, maybe,
uh,
but maybe that would be a little too generous. And then there's this, a student says, a bunch, two different pairs of galaxies. These are round, these are longish, this one doesn't, this has arms. This is clearly what level of reasoning?
um, very basic.
Yeah, this is egocentric. What
Yeah.
what Piaget, in the terminology of Piaget, this is egocentric. Uh,
Well, I learned it as pre-operational, I guess. So,
Pre-operational. Okay, and here's a little summary chart of what we've been talking about. In the frames of reference, an egocentric can only imagine their own point of view. At the concrete level, they can imagine another point of view, but only after a concrete experience. And then formal level, they can imagine all different kinds of points of view. In the scientific explanation realm, the ecocentric uh, attributes motives and purposes to inanimate objects and assumes that phenomena are produced by human actions or for human purposes. Concrete level, they can have more complex relationships between the elements, and they can incorporate new observations to revise their explanations. And at the formal level, they can extend explanations to predict new observations. And then in the classification that we just did, the egocentric level, and these are Piaget's, terminology. We can use different terminologies, but they notice similarities and differences. Concrete level, they can classify by a single trait, and recognize objects may belong to more than one class and arrange things along a continuum. And then formal level, they can arrange things in a hierarchy and rearrange them fluently. So to wrap up a little bit here, I wanted to mention a way that idea of a concrete experience to learn about moon phases. And this is something that you're probably mostly all familiar with. Uh, it's the moon ball activity. You know what? This is an activity. Well, okay. First of all, just to recap a little bit what I said earlier, it's a good idea to have your audiences discuss their ideas about a subject before you attempt to teach it. It's probably something I didn't do in this workshop. Didn't I didn't exemplify that. But ideally you do it in a very brief. It doesn't take long to do that, but you want to take long enough to identify a few different alternative viewpoints, if possible. That gets them thinking that there are alternative viewpoints. And of course, remember that a good way to initiate an interaction is to ask a question. And in the three examples we had, we were looking at the appearance of moons from the surface of Mars as a question. We looked at the path of a rock dropped through a hole in the Earth, and the question was, how is that going to behave? And then the question of why the moon appears to be different shapes. So focusing on a question. This activity is that we developed that I mentioned it in the Great Explorations in Math and Science, the GEMS activity of From Earth, Moon, and Stars, which was a teacher guide that actually was derived from the Planetarium show Moons of the Solar System, which is part of the planetarium activities for successful shows. That's all on the website, that I will give you the URL to momentarily. But I wanted to just mention that how many of you have used moon balls as an activity for explaining phases of the moon? Yeah. Let's see. Actually, Rosemary, if you could sort of shift your view, and if everybody wants to shift your view, so hopefully you can see me with this moon ball. Actually, let me just turn off the slides for a second. This won't take too long. Stop my share. And I'm holding a moon ball. And this is hard to do in a virtual situation here. But basically, we need to shine a light on the moon. And it's hard to do when you don't have a dark room, which I don't have here. But I'm shining a bright flashlight. But if I'm on a swivel chair, I can swivel around here and change. Does the phase of the moon seem to change for you as I,
Yeah, that's very cool.
yeah.
Very simple
Yeah.
but elegant.
So this is a, well, I'm not, you can, this is a real wake up for a lot of people, even adults, when you have a single light in the planetarium and the whole planetarium's dark, then that is a very effective moon, more effective than this flashlight here. But then each person has their own moon and they are looking at it from an egocentric view. Okay, I am the Earth, that is the moon, and I'm looking at the sunlight shining on it. And that's probably the most effective way of teaching about moon phases. And in the planetarium show, that happens after observing the moon for a couple of weeks to see how the phases change every 3 days or so. That's the observing the moon model before doing the model. Um, so
I was just going to say there's a modification of this one can do also, where you're standing outside and you use the sun as your light source. And that when you have the moon at quarter phases, you can talk about the shadows and how shadows have nothing to do with it. Because you simply say, where's your shadow going? Your head is the earth. With your head as the earth, where does your shadow go right now? And it's going off in one direction. And the moon, meanwhile, is 90 degrees off of that direction. You say, so you see your shadow has nothing to do with it. So therefore, the earth's shadow has nothing to do with it. That's one way to douse that particular flame.
excellent. And the sun is probably the best possible light source you can possibly have.
Well, the other thing about that is if you can do it when the moon is in the daytime sky, that really cements things because their ball will match the moon phase. And what I like doing is the old ASP activity that has different views of the moon at different times, but it's not at the precise phases. And you have them put those in order first without teaching them, and then you teach them, and then you have them do that same activity again. This is fresh because I just did this with a group at a summer camp.
Excellent.
Nice.
Excellent.
Or you can also have a series of phases of the moon and ask students to determine what time of day it is or night.
Yeah.
Yeah, that's
Well,
I
Time
like
of the
to
moon.
take
the good thing about doing the activity where there's no clear phases is another thing you can point out to them after they do it too is, did you try to figure out which end of the moon was up and place them consistently? Because they'll be able to see different mare on the moon, and did they place them consistently? And that's another test of a level of reasoning that
that's
that
a
you can kind of turn them on to.
frame of reference issue in terms of this workshop. Okay, so in the home stretch here, I only have a couple of slides left. Uh, uh, well, this activity, I said that each person has their own moon ball, so they have an egocentric view of it. And in general, it's a good idea to get people to realize what people are reasoning, where they're starting at with their reasoning, and then start with something familiar to them so that they can get involved in interactions in the workshop. In the Martian moon problem, it's easy for people, and you probably noticed this, it's easy to select the right phase for Deimos, but then you have trouble with Phobos. And we ask how are the two problems similar or different? Well, solving the first problem may help them solve the second problem. So that's a strategy that can be used in other situations. Start with an easier problem that can then lead to a more complex problem. So overall takeaways from this workshop, in my opinion, I don't know if you got this out of it, but that many people approach astronomy problems with concrete or egocentric reasoning, and they can't engage unless you realize they are starting at that level. Some topics can be understood with concrete or egocentric approaches, and others require more formal reasoning. So we need to select our topics for the level of audience we have. And if possible, switch streams actually if you find out that you're operating at the wrong level. And then that's basically what point 3 is, that you may need to switch streams if you find out that if a person is engaging in a topic which is comfortable for them, they can grow from that better. Another thing that I might add in here is that thing that's in the lower right. It's unrealistic to expect people to give up explanations that satisfy them without a struggle. Okay, so we need to be realistic in our hopes with this, and it's easy to be frustrated as an instructor or as a planetarium presenter. But if you realize that, well, if you just make a little bit of progress towards increasing their understanding, that's good. That's something to be happy with. What we don't have time for, that is part of this workshop, and I leave it as a homework for you, which will never be checked, um, is a challenge. Oh, actually, this first paragraph is what I just said. They can be disheartening, and our job is difficult, but it's more realistic to expect people's ideas to be a little closer to the scientific viewpoint after an activity. Then we don't need to expect them to understand the concept completely. This challenge is probably one of the toughest ones. Design a school planetarium, classroom, or outdoor experience for students to be able to provide a formal level explanation for the seasons by the time they reach high school. We are not going to do that in this workshop, but we would want to do it at 3 different levels: for first graders, for fifth graders, and for 10th graders. And that's an interesting exercise to go through. I leave that as your final. If you come up with that, please email me. Please email me how you did it. And all these are references. That's my email address if you have questions or want to follow up in any way. The Planetarium Activities for Successful Shows has not only the Moons of the Solar System show in it, which has that moon, was where the moon ball activity derived from, although I don't think we really invented that. I think it probably came from somebody over in Glippa, probably. Um, and then there's 3 different places to get it on the web, and I will copy. I'm momentarily going to copy these and put them in the chat. But the Planetarium Educators Workshop Guide is there, and the slides that I used. There's a URL for the slides that I'm using. So let me just stop my share, and I will copy those into the chat. Okay. And thank you for coming to the workshop. It was almost an hour and a half workshop instead of an hour. Not too bad. Okay, but
Thanks, Alan. Thank you.
yeah. Okay, I promised I would put it in the chat. Just a second here. I got it. Almost have it. There you go. And thanks again for coming. This is
If I may, a couple of moons ago, probably about 98, 99, a teacher who was doing a master thesis on misconceptions in astronomy approaches us at the Science Center to make her study for the thesis. So she had a questionnaire for before the planetarium session and another one for after the planetarium sessions. And the first sessions were specially designed to find the students' misconceptions. And then there was a follow-up that how to make them deconstruct their misconceptions. So basically to fix their universe. One of the things that I found on that was uh, it was transversal. It was about we could use the same techniques for different school levels.
Mhm.
The things that worked for the little ones would also were also the ones that worked best for the older students.
Hmm.
That was something that surprised me.
You know that I said earlier that a lot of times even people operating at the formal level get a lot of benefit from things that are designed, to work for egocentric or concrete level learners. So that I can understand that completely.
And
And
touching on some of the slides you showed, there is one thing about the sun and the moon, because as that misconception that the moon is only seen at night. Uh, it goes. I found it goes a bit further than that. The idea for most of the students, especially for the smaller ones, was that the sun creates the day, the moon creates the night. You cannot have a
ah,
night without a moon.
that's interesting. Yeah. Well, and in mythology or legends, that's always the case that the moon is responsible for night and the sun is responsible for day. Yeah.
So
Go ahead.
maybe kind of along that line of deconstructing. I mean, what struck me is that where I live, it's cloudy most of the time, and students, especially on the younger side, they go to bed early. They have limited views of the night sky. Either in summer it's too light, or it's too cloudy during the rest of the year, or they're asleep. So first it'd be good. And then, older students, maybe they just don't look up. I mean, there's lots of reasons, but students have conceptions based on what they've observed and internalized. But modern digital planetariums can provide a set of observations, like different times of day, Paris versus where they live on the same day. Does the moon look different or the same? I mean, you can provide a bigger set of observations for them to start to draw conclusions from before you even get to the physical explanations of the physical motions and so forth. But I think it all depends on whether students actually trust the planetarium to be a reliable, truthful source, because computer games and simulations can be just anything you want. So they first have to believe that what I'm telling them and showing them is actually physically true, I think.
Wow, that's heavy, heavy, Rosemary. They they believe
So
that.
am I. I don't I mean, my
Okay.
kids, they haven't seen much. So I don't think I can go straight from what they have seen to how things move, because they don't have a database of observations to match that to. But
Well,
So
I'm
anyway.
they go home and tell their parents what they learned in the planetarium, and if their parents don't agree with it, then they tell them that that's not true. And just
yeah, they get conflicting input. Well, especially for some in religious conflict topics.
exactly.
That's that can be a conflict for the student if we're telling them one thing and their parents telling something else.
Well, and life is like a game of telephone too. They'll misinterpret what we say, and then their parents will get a different impression, and then you'll have to solve it again. Hopefully, when they come back to the planetarium or some other time.
But I think the models, a model that they can play with is very powerful. So the parents might say that this is, that's wrong, but I think the student will know that, oh, well, this is what I saw with my model, and so even with the drag of a parent's misconception, they will have one more thing to allow them to advance. That's all we can do, I think. But the heaviness that I was referring to, Rosemary, was the idea that people do not trust science.
Yeah. Oh, okay.
That's what I was flashing on, and then we're
Yeah.
encountering that societally. It was always there, but we seem to be hitting on it especially hard right now.
Well, and there's always the Northern
Indeed.
Hemisphere bias, and also probably you deal with this, Rosemary, a mid-latitude bias
Yeah.
in
Yeah.
what we
The sky
teach.
can do strange things here. I mean, sometimes it's nice to point out how northern latitudes are different, special, but I don't know. I think there's at least what I'm thinking now is there's a place for letting students experience different situations as observations. Hopefully, they believe that the planetarium is doing accurate representation of being different places at different times, so that maybe they can start to draw different conclusions from just the few random observations they have from where they live. Just a thought.
Yeah, the your idea that the power of the planetarium to be as a time machine and location mach to be move different places is especially powerful in modeling, not modeling, well, it is a model of where the behavior of the sun at different latitudes. You know,
Yeah,
there's the classic activity that we've done about guessing where the sun is going to set given where it
yeah,
rose. And it's really startling what happens at your latitude, Rosemary, for most people who don't
yeah,
live at your latitude.
yeah.
And the land of the midnight sun.
Which I'm not quite there.
Yeah, yeah, no,
but
you're not quite there.
but part of the state is.
Fairbanks is a little closer, but
Yeah.
Juneau is pretty up there. Up. Now there's an is Juneau up there or is it?
Well, that's what's nice about that solar motion um, activity that you showed me, Alan, where it works for all latitudes.
Oh yeah, the solar motion demonstrator.
Yeah, exactly.
Yeah, that's pretty cool device. That was invented by Joe Snyder at Oberlin College, and he gave us permission to he gave us permission to put that as a classroom activity for our Stonehenge program, which is, I think, I'll have to double check, but I think that is in the past series. I need to check to make sure that it's in the classroom activities section.
Yeah, I'd like to find that one.
The solar motion demonstrators.
Yeah.
Yeah, we have a solar calendar here that used to be called the Cesar Chavez solar calendar. And the guy who initiated that was horrified with the recent revelations about how Chavez was not the most virtuous as he thought anyway. And at that, I do activities out there, and the solar motion demonstrator is one of the things I use to illustrate, how the sun behaves at different seasons. It's really effective. We didn't stop recording, did we?
No, we're still recording. I just wanted to say I really appreciated the discussion today.
Yeah. Yeah, I hope
We
I
could
didn't.
stop the recording anytime, but I think there was still good discussion going on, so it's fine.
Yeah, and I hope I didn't make any political allusions here. I think
don't
I
think
did
so.
actually, but that's okay.
Only
It's mostly for the United
things in the
States,
newspaper.
actually. Yeah. Yeah,
Yeah.
Dario, you don't have to worry about it. It's the United States.
Okay, so I wonder, does anybody else have any questions? Feel free. If you want us to stop the recording now, we can also do that.
I think it's safe to do
Yeah,
so.
let's do that.